Hi everyone, welcome to Math TV with Professor V. In this video, we're going to talk about how to determine whether or not an infinite sequence converges or diverges. Now, a lot of you at this point in Calc 2 are studying sequences in series, and there's a lot of emphasis on testing for convergence or divergence of series, but let's not neglect the building block of infinite series, which are sequences. So let's work on how to figure out whether or not these are convergent or divergent. The main crux or the point of this video is just to bust through a bunch of examples and give you a lot of exposure to different techniques. But if you want a full lecture on infinite sequences, I'll link it here. But basically, what do we mean when we say a sequence converges? Well, the sequence an has the limit L if the limit as n approaches infinity of an is equal to L being a finite number. And so a sequence is convergent if the limit as n approaches infinity of an exists. So basically, you take the limit of the terms of the sequence, and if it approaches some finite number, then we have a convergent sequence. A sequence is divergent if this limit does not exist or if it's plus or minus infinity. Okay? Now, what we need is a strategy because you're going to use a variety of techniques. So let me just bullet some points, things to try. So here's your strategy. First thing, just take the limit directly. So you take the limit as n approaches infinity of an directly, and you hope that you get a number or infinity, negative infinity does not exist, and you're done. If that doesn't work, okay, some other things you can do. You can define a function that is basically equivalent to your sequence, and then you're going to use L'Hopital's rule if you have the case of 0 over 0 or infinity over infinity, etc. Another option is you can apply the Squeeze theorem or sandwich theorem. Usually that'll come up when you have sequences that involve sines and cosines because they're easily bounded. And the last thing you can try to do to show a sequence is convergent is to show that it's monotonic and bounded. Now, there's a whole nother discussion that needs to be had about that. So I'll link a video here where I do it precisely, said discussion. Okay, so let's just jump into some examples. We'll warm up with some easy ones, and then we'll kick up the spice level at the end. So here we go. Determine whether the sequence converges or diverges. If it converges, find L. So I'm just going to start off, take the limit as n approaches infinity, and see what emerges. If this doesn't work out for me, then I'm going to go through my strategy list, okay? So here we have a rational expression, rational function. Divide by the highest power of n that you see in the denominator. So in this case, that would be n squared. So I'm going to divide everybody by n squared. And then in the next step, let's see what we got. So we've got limit n approaches infinity. In the numerator, I'm going to have 3 over n squared plus 5. N over n squared, that's just 1 over n, and then plus 1. All right, so as n approaches infinity, 3 over n squared, that's going to go to 0. 5 is just a constant. And then 1 over n also approaches 0. So all we're left with is 5 over 1, which is 5. So that's my limit L. That's a finite number. So that tells me that this sequence converges. And that's it. Okay. Let's look at another one. See, they're not so bad. The sequence an is n to the 4th over n cubed minus 2n. So we're going to take the limit as n approaches infinity. This is always my first go-to. Just take the limit of the terms. See what's happening. N cubed minus 2n. Now be careful. You only divide by the highest power of n from the denominator, not overall. No, no, no. So highest power of n from the denominator, again, is n cubed. So let's go ahead, divide by n cubed. And now we've got, let's see, limit n approaches infinity. N to the fourth divided by n cubed is just n. N cubed divided by n cubed is 1 minus, I'm going to have 2 over n squared. So now let's see what's going on. As n approaches infinity, the numerator has an n, so that's going to go to infinity. Denominator, 1 is just a constant, minus 2 over n squared, that's going to go to 0. So now I have numerator approaching infinity, denominator approaching 1, a positive constant. So this limit's going to be positive infinity. Well, that's a limit, but it's not L because L is only defined to be a finite number, okay? So this sequence diverges and we leave it alone. Okay, look, see, we're surviving, we're thriving. Let's move on to example 3. an equals 3 to the n times 7 to the negative n. I'm going to rewrite this sucker, okay, before I take the limit. This is 3 to the n over 7 to the n, which I can rewrite as 3/7 to the n. Okay, now let's take the limit as n approaches infinity of 3/7 to the n. This limit, hopefully you're familiar with it. This is a geometric sequence. And the common ratio, r, is equal to 3/7, which is less than 1. So this limit is going to be 0. Why? Let's think about it. You're taking 3/7, something smaller than 1, and you're multiplying it by itself infinitely many times. It's going to keep shrinking, 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 approaching 0. And that's the case for any geometric sequence when r is less than 1. So that's our limit L, and we can say that this sequence converges. That's it. Okay. Example 4, an equals e raised to the negative 1 over rad n. So here we go. Let's take the limit as n approaches infinity of e to the negative 1 over rad n. E raised to the x is a continuous function. So I'm going to apply one of my limit laws for sequences and pass the limit through to the exponent. So watch how I'm going to rewrite it. It's so slick. You have e raised to the limit as n approaches infinity of negative 1 over rad n. Okay, so let's see what's going on here. As n approaches infinity, denominator is getting really, really big. So negative 1 over rad n, that's going to approach 0. So now for my limit, I'm left with e to the 0, which is 1. Well, that's a finite number. That's L. So this sequence converges. Okay, good. Let's look at another. Example 5. an equals square root of 1 plus 4n squared over 1 plus n squared. Every single time, start off limit, n approaches infinity. Square root, 1 plus 4n squared over 1 plus n squared. So similar to the last example that we did, we're going to apply our limit laws, and I can pass the limit underneath the radical. Since n is approaching infinity, positive infinity, right? Always with these sequences. I know that the radical is going to be well defined. I'm not going to have any negative values underneath, so I can pass that limit underneath. And now let's see, we've got 1 plus 4n squared over 1 plus n squared. Plus everything's squared under the radical, so we're super duper safe. Now I'm just going to focus on this rational expression. Let's divide numerator and denominator this time by n squared. That's the highest power of n in the denominator. And then we've got here square root of the limit as n approaches infinity, we will have 1 over n squared plus 4 over 1 over n squared plus 1. Beautiful. So as n approaches infinity, these 1 over n squareds go to 0. And I'm just left with 4 over 1 underneath the radical. But that's just square root of 4, right? Which is 2. That's a finite number, so that's L, and we can say that this sequence converges. Okay, now before we move on to the next couple examples, I wanted to show you or remind you of a theorem. It states if the limit as n approaches infinity of the absolute value of an is equal to 0, then the limit as n approaches infinity of original an without absolute value is also equal to 0. And I explained this more a little bit in the lecture why that's the case, but basically if you take the absolute value of the terms and they approach 0, that means they're shrinking in magnitude, right? Absolute value makes everything positive if it isn't already, or 0, worst case scenario. So if the limit of everything when it's not negative shrinks to 0, then even if the terms bounce between being positive and negative, they are shrinking in magnitude and will approach 0 as well. Why am I reminding you of this? This is great to use anytime you have an alternating sequence. So use this theorem when an involves -1 to the n or -1 to the n plus 1, and then it has some other stuff. Okay, like the following example right here. So an equals -1 to the n times n plus 1 over 2n squared plus 3. So how would you write this up properly? I will show you. You should say consider the absolute value of an, which is equal to the absolute value of -1 to the n of n plus 1 over 2n squared plus 3. Well, what does taking the absolute value do? It basically eliminates this alternating portion, because now -1 to the n, it just bounces between +1 and -1, depending on if n is even or odd. But if I take the absolute value, then they're all positive. So goodbye to that. So then we're just left with n plus 1 over 2n squared plus 3. So now let's go ahead. I'm going to take the limit, not of the original sequence, but of the absolute value of an. And let's see what happens. I'm feeling optimistic. Limit as n approaches infinity of n plus 1 over 2n squared plus 3. Now, how do we take this limit? Don't even say L'Hopital's rule, because then we have to define a function and it's so much more work. So we're going to divide by the highest power of n in the denominator. Divide by n squared. And then let's see, we've got the limit as n approaches infinity. N over n squared, that's 1 over n plus 1 over n squared. And then down here we have 2 plus 3 over n squared. Okay. 1 over n's going to 0. 1 over n squared also goes to 0. Same as 3 over n squared. So all I'm left with now is 0 over 2, which is 0. I'm so excited because remember, what did my theorem say? If the limit as n approaches infinity of the absolute value of the terms is 0, then the original limit as n approaches infinity of the sequence is also 0. So now I can answer the question. So I can say this implies by said theorem that the limit as n approaches infinity of the original -1 to the n times n plus 1 over 2n squared plus 3 equals 0 also. Convergent. Now, why did I freak out at you right now about L'Hopital's rule? Because L'Hopital's rule can only be applied to differentiable functions. Sequences, I'm so sorry, they're not differentiable, right? These are points, a discrete set of points that are not continuous. So you can't apply L'Hopital's rule unless you define a function basically equivalent to the terms of the sequence, and it's just a little bit more work. So I tried to save L'Hopital's rule for only when it's very, very necessary. Okay. Now, this worked out conveniently for us because this limit was 0. Yes? What if it is not? What does that tell you? I will show you. It actually means the sequence diverges. But how do you write it up nicely? Observe the following. So here's something very similar, a sequence I made up. We have an equals -1 to the n times n plus 1 over 2n plus 3. See, what's the only difference between this example and the one before? The n is not squared in the denominator. Oh my, that's going to change everything. So absolute value of an, absolute value of -1 to the n times n plus 1 over 2n plus 3. All that happens is that alternating portion's gone. So now we just have n plus 1 over 2n plus 3. All right? So now we're going to say, let's consider the limit as n approaches infinity of the absolute value of an. So the limit as n approaches infinity of n plus 1 over 2n plus 3. Same as before, I'm going to divide by the highest power of n from the denominator, but that's only n to the first this time. Oh, look how things are going to change. So now we have the limit as n approaches infinity of 1 plus 1 over n over 2 plus 3 over n. Let's see, as n goes to infinity, 1 over n will approach 0. 3 over n, where does that go? 0 also. So all I'm going to be left with is 1 over 2, and that makes me very sad because that's not 0. So what can I say now? An actually is a divergent sequence, but we haven't justified that fully. Look at what's happening here. It's oscillating, yes? So if you consider the even terms versus the odd terms, you'll see precisely what's happening. Okay. Even terms are all of those, like the second term, the fourth term, the sixth term, etc. So the even terms are defined by a sub 2n. They would be -1 to the 2n. I'm just substituting now 2n for n here, yeah? Okay, good. And then we would have 2n plus 1 over 2 times 2n plus 3. Well, what results? Well, -1 to the 2n is just going to be +1 because you're always raising it to an even power. So you're just going to have 1 times 2n plus 1 over 4n plus 3. And it's not hard to show, let me just get this out of the way. It's not hard to show that the limit as n approaches infinity of a sub 2n of these even terms is going to be +1/2. The odd terms are going to be defined by a sub 2n plus 1. So that would be -1 to the 2n plus 1. Now this is going to get a little spicy in the numerator, but you can handle it. It would be 2n plus 1 over 2 times 2n plus 1 plus 3. Well, what does that tell us? Move, I need some room. -1 to the 2n plus 1 is always going to be -1 because you're raising it to an odd power, okay? So then you would have -2n plus 2 in the numerator over, this would be 4n plus 5. And it's not difficult to show that the limit as n approaches infinity of the odd terms is equal to, see now how this negative stayed? A -1/2. So basically, there's another theorem when you study more advanced calculus that every subsequence in a convergent sequence must converge to the same limit. So since we have the even terms approaching +1/2 and the odd terms approaching -1/2, they're oscillating. Yes, it's bouncing around. So just imagine it's like this. Here's +1/2. Here's negative 1/2, okay? And in the beginning, the terms are big, and then they shrink, but then they just keep bouncing like this. Bouncing, 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 bouncing. So the limit doesn't exist. It's a divergent sequence. The theorem is specifically tied to 0 because only positive and negative 0 are the same value. So that's why when you take the absolute value, if the terms shrink, 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 and they're still bouncing, but they're getting close to 0, then we're good, right? The problem is when they approach a number other than 0, odd terms go one place, even terms go one place. So now that you've shown that the even and odd terms have different limits, then you can say this means the limit as n approaches infinity of an does not exist, actually. It oscillates, so it's divergent. That would be a full credit answer in my class. I don't know how picky your professors are, so check with them, okay? Fabulous. Next one, sequence an is equal to sine of n. I mean, there's not a whole lot to say. Do we remember what the graph of sine looks like? I hope so. It's oscillating. Now, I know this is a sequence, not a function, but sine of 0 would be here. Sine of 1, it's less than pi. Sine of 2, well, anyways, it's going to follow this shape. It's just going to be, you know, distinct points. And so it's oscillating, and we can just say that the limit doesn't exist. How much work do you have to show? If you were in my class, you can just write the limit as n approaches infinity of sine n. It does not exist. It oscillates, if you want to write that down. Therefore, the sequence is divergent. It's bouncing around. It's bouncing around like a maniac. Okay. Let's look at a couple more cases where we can employ some of the methods I listed in the beginning of the video. So here we have an equals n squared times e to the negative n. I always like to rewrite these negative exponents in the denominator just because it helps me get an idea of what's going on better. So let's try to take the limit directly. Limit n approaches infinity, n squared over e to the n. It's not our typical rational expression where you just have like polynomial in the top, polynomial in the bottom, right? We've got that e to the n. And as n approaches infinity, numerators approaching positive infinity, denominators also approaching positive infinity. So we actually have an indeterminate form of the type infinity over infinity. So it would be a beautiful moment to apply L'Hopital's rule if only we were dealing with differentiable functions, and we're not. Sequences are definitely not differentiable. So what do? Well, you're a precise mathematician, and you say, let f of x equal x squared over e to the x. I'm just swapping out n's for x's. This is going to be a differentiable function. So now we're going to consider the limit as x approaches infinity of x squared over e to the x. I already have established that we have an indeterminate form of the type infinity over infinity. So I can apply L'Hopital's rule. And now we have the limit, as x approaches infinity. Derivative of x squared is going to be 2x. Derivative of e to the x is still e to the x. Well, I still have numerator approaching infinity, denominator approaching infinity. So let's apply L'Hopital's rule one more time. And now I have the limit as x approaches infinity of 2 over e to the x. Ooh, yay. So 2, that's just a constant. E to the x is approaching infinity. So constant over infinity, that is going to approach 0. So since the limit as x approaches infinity of f of x equals 0, then we can say that the limit as n approaches infinity of n squared e to the negative n equals 0 also. Therefore, it's convergent. And its limit L would be 0. All right, you have to be precise. I know it might feel silly, like all I'm doing is swapping out n's for x's. Well, too bad, okay? You're not allowed to use L'Hopital's rule unless you have a differentiable function. So just be glad we at least have L'Hopital's rule. It's just a couple seconds of your life. Okay, here's another. an equals cosine squared n over 2 to the n. So if you try to take the limit directly, okay, cosine squared n, just think it's the same as cosine of n squared. And we know that cosine and sine, these oscillate. So the limit of the numerator doesn't exist. 2 to the n, that's going to approach infinity. And you might think, okay, so it's oscillating. I'm a little stuck there. I can't really use L'Hopital's rule because if I keep differentiating cosine n, I'm just going to keep getting back sines and cosines, sines and cosines. So it's not going to help me. Maybe we should try the squeeze theorem because cosine can be bounded, right? So it's actually cosine squared. Normally we say cosine of n is bounded between 1 and -1, right? But if I square cosine, it's never going to be negative, right? Worst case scenario, the smallest it's going to be is 0, and it's still less than or equal to 1. And then I'm trying to squeeze the limit. So I'm trying to make the expression in the middle that's being squeezed match what this sequence is. So I'm going to divide everything by 2 to the n. And 2 to the n is not negative, so I don't have to worry about the direction of the inequalities getting flipped or any of that, right? Be careful. Since 2 to the n is greater than 0, the inequality is preserved. 0 divided by 2 to the n is still going to be 0. This is, I'll write it to match the way it is in the problem. And then we have 1 over 2 to the n. So what does the squeeze theorem tell us? We'll take the limit of the lower bound. It's just a constant. Take the limit of the upper bound. 1 over 2 to the n. Well, 2 to the n is going to infinity, right? 1 over something approaching infinity goes to 0. Notice these are equal. So that tells us by the squeeze theorem, fabulous things. Therefore, by the squeeze theorem, let me actually add a page. By the squeeze theorem, the limit as n approaches infinity of cosine squared n over 2 to the n equals 0 also, and therefore it's a convergent sequence. And that, I don't know if you can hear the little chiming music in the background. That was my wake up alarm. I woke up about 2.5 hours before it. I was so excited to make this video for you all. So I'm actually going to end it here. We'll just do a part 2 with more examples. Okay, I'll turn off my alarm, get on with my morning. I have to do a workout. You know, we do all the things over here. I hope you get some fitness in your life too. It's very good. And give the video a thumbs up if you found it helpful. If you would like a part 2, please comment down below. If you feel like you're over sequences, you want something else, let me know too. That's totally cool. If you want access to exclusive content, quicker responses to your comments, etc., etc. If you're about the VIP life, then click the join button. You can become a member to this channel. Also, you can catch me on Instagram and TikTok at MathTV with Professor V. I have all sorts of fun there. So stay tuned, you guys. Subscribe and give this video a thumbs up if you haven't already. I'll see you all soon.